Hi, everyone. Thanks for being here. I'm Palak. I'm a product manager on Google Kubernetes Engine. And I have with me Ken.
Hi, I'm Ken Owens. I'm a software engineer on Google Kubernetes Engine. I work on the Workloads team. And in open source, I contribute primarily to the Workloads API. That's in the special interest group applications. And I'm a co-chair of that group.
So today, we'll talk about how to build portable data processing workloads on Google Kubernetes Engine. The amount of data that companies are dealing with is exploding. Information is a valuable commodity. There's an increasing need to generate relevant and intelligent insights from that data to make business-critical decisions. But doing so is not easy, especially when you're dealing with a humongous amount of data and tools and technologies that are changing at a rapid pace. Users need a way to incorporate intelligent decision-making in their applications while iterating quickly on their applications. They also want to use the latest machine learning and data processing technologies in a way which is easy to understand and doesn't have a very steep learning curve. Developers need to offload the operational burden of actually deploying and managing an application in production clusters, while at the same time, they are asking for high performance and acceleration to get intelligent insights at a lightning pace. Enter containers and Kubernetes. Containers are sealed deployment units that provide efficient isolation, reusability, and portability. Through containers, you can modernize your infrastructure and launch and iterate on features much faster. Kubernetes has emerged as the leading container orchestration platform. It does all the heavy lifting for you for managing, operating, upgrading, and scaling your production clusters. Moreover, it is open source, so you can move your applications and workloads to any cloud without any vendor lock-in. Today, we will talk about how Kubernetes provides the best platform for running those data processing applications. We will show you a demo and a technical deep dive on both Spark and Airflow applications on Kubernetes. Over to you, Ken.
So today, I want to talk a little bit about the pieces that you use to build a data processing application on top of Kubernetes. How many of you guys are familiar with pods? Most of you. So most of you have used Kubernetes or have some experience with it. OK, so this might be a bit of an overview for you. So Kubernetes is all about resources. Like when you create a pod, a volume, whatever, it's mirrored by some real object or some object in storage inside of the system. At the base, you've got a pod. This is your atom of scheduling, resource allocation. It's basically a loosely or tightly coupled set of containers with a shared namespace, shared networking, and volumes. And they have a shared lifecycle. They live together, they die together. Usually, you only run one container per pod unless you've got sidecars, but sometimes you run more than one. So volumes, PVs, and PVCs. These are the atoms of durable storage, right? So a volume is basically something that appears inside of your pod on the file system. You can use it to access your data. If it's not backed by a PV, then it's ephemeral. It disappears and the pod dies. If it is backed by a PV on Google Cloud, it's backed by a persistent disk. When the pod dies, your data is still on the disk. PVCs are the way you associate those PVs. It's the way you provision those PVs. It's the way you get your volumes into your pod and get your data off. That's interesting, but you also need to get data across the network into a pod. To do that, you use services. And this is basically the atom of networking. It programs the network to route traffic to pods. And it may provision load balancers if you expose it externally. So pods, it's the basic workload you can run, just one single pod, right? But it's not very interesting. In comes the Workloads API. So deployments and replica sets, these are for your 12-factor apps. Might not be interesting for data processing in specific, like your core data processing workloads, but you still need 12-factor apps in order to access those workloads, in order to have administrative consoles. And all a deployment is basically, I'm going to replicate this pod in an identical way n times. And when I update it in a consistent manner, but I can do it concurrently. So if I have 3 pods, I can update 2 at a time. Not particularly good for databases, not particularly good for stateful applications in general. That is why we created stateful set. So stateful set creates M pods in the same way a deployment does, but these pods are different in that they have durable provision storage, and they also have a durable network identity. And what that means is if you kill the pod and you bring it back, it gets the same storage. It gets the same CNAME, it gets the same SRV records. The rollouts are slightly different too. They're not concurrent. They're ordered and sequential. meaning that if I have 3 pods, I wait till pod 1 is running and ready before I launch pod 2. If pod 2 dies, I don't kill pod 1 until pod 2 is completely terminated. And then daemon sets create 1 pod for every node in the cluster. From a perspective of data processing, if you're running something like HDFS or any other distributed file system, your data nodes, you want to put them on a particular set of nodes in the cluster. You don't want n of them. When a new node comes up, you want a new data node. Daemon sets allow you to do that. So those are all interesting from the perspective of workloads that run continuously. The pods of a stateful set, they never, well, if they do terminate, they get restarted. Same for a deployment, same for a daemon set. But with bachelor workloads, you have a difference, right? They run to completion. If I start a Spark job, I want the job to eventually stop running. When it's completed, maybe I want it to restart if it failed. That's where job comes in. Creates pods that run to completion, counts the number of successes, and once a specified number of successes have occurred, the job terminates and it says it's completed successfully. And cron jobs are just a way to manage time-based jobs. You can do one-offs, you can do repeating ones that run at a specific interval. So the one thing we realized when we were building the Kubernetes API is that we can build you primitives, but we can't build every primitive you're ever going to need. So none of the resources are actually special. You can bring your own resources. These are custom resource definitions. And it basically allows you just to define your own resource. I think if you define job as the resource that we use for the batch v1 job, you can create a Spark job. You can create an Airflow cluster. And these become part of the API in the same way, fundamentally the same way as any other resource. To act on them, though, you need to bring a custom controller. So all the resources that we've talked about so far each have a controller that ships with Kubernetes. But you can easily install your own controller to act on the resources you define. So we've talked a lot about the pieces of these data processing pipelines. The question is, how do I get those onto my cluster? So one way to do this is using manifests. And a manifest is basically just a YAML file that contains most of those atoms that we talked about before. You deploy it, you apply it, it runs, and it creates the workload for you. The problem with this is, if you're trying to get something off of the shelf, like go get a YAML file that somebody else has created and deploy it into your cluster, what if your monitoring solution isn't the same as the one that was found online? Or what if your lifecycle management solution is totally different? The manifest isn't really portable from that perspective. So in comes Helm. Now, Helm is a Kubernetes package manager. And what it allows you to do is to template those manifests and apply a set of values to them. So it still doesn't solve for lifecycle management, but let's say you have a template for the logging solution. You can just plug that in via values.yaml. If you want to change configuration, a values.yaml will allow you to change that. But really for complicated orchestration, which is typically the use case we see for data processing, it's still not sufficient. So if you combine a custom controller with a custom resource, you get what's colloquially called the operator pattern. So the operator pattern is basically, I'm going to teach my cluster to understand what a Spark job is. Then I'm going to write a controller to act on that Spark job. And I'm going to encode the day 1 and day 2 operations necessary for keeping that cluster up inside of that controller, inside of that operator. And that seems to be the dominant way that we're approaching the problem. My colleagues are going to give you some demos later on contributions that we've made to the community in particular for this.
Cool. So just diving a bit deeper into operators. For users to really trust Kubernetes to run production workloads like databases, it needs to be super easy to automate it. And the way to scale it is to actually automate how you manage it. An application operators or an operator is basically like a robot which performs some of those functions of an app's ops group. Think of a DBA, how critical a DBA is to the enterprise. So this is really useful for stateful applications. They encapsulate the operational concerns of running an application on Kubernetes. And they run these applications in a declarative fashion, which Kubernetes understands. The control loop observes the existing state. It looks at what the desired state is. It sees what the difference is needed, and then acts upon the system to actually reach that desired state. Now I'll talk about how Google Kubernetes Engine is providing some of the best tools and technologies to run those data processing workloads. We recently launched a marketplace called GCP Marketplace and recently launched the Kubernetes section within it. So what that means is now the GCP Marketplace has native integration into GKE. You can click to deploy stateful applications on GKE, view those applications on the UI as well as on your console. We made available first-party Google-developed solutions like Spark and Airflow to start with, as well as several third-party solutions by vendors. Besides that, we have also been leading the open source efforts to develop something called an app resource. Previously, there was no concept of an application in Kubernetes. There were a bunch of workload controllers like deployment sets, stateful sets, and others, but we didn't define an application. With this app resource, you can now view and manage your application effectively on Kubernetes. You can also leverage some of the cutting-edge data services that GCP provides. For instance, BigQuery, Cloud AI, Stackdriver, TPUs, and GPUs. You can natively integrate those on your Kubernetes applications on Google Kubernetes Engine. So the first operator that we launched was the Spark operator. We had seen from users that many of them want to run data processing and batch analytics workloads on Kubernetes in a way which is native to Kubernetes. They wanted to use kubectl when running their Spark jobs. The Spark operator is available on GitHub as well as on the GCP Marketplace. And I would like to invite Yanan Lee, who leads the Spark operator, to give a demo and talk more about the operator.
Thanks, Palak. All right, so let me actually switch to, OK. So before I start, just want to get a sense, like, how many of you run Spark on Kubernetes as already? OK, quite a few. OK, hopefully the number will get bigger, after the talk. So, well, the Spark operator is basically a project that follows, the recent operator pattern. So at its core, there's, some custom resource types and also the corresponding custom controllers that, extend the Kubernetes API and control plane with application domain knowledge. In this case, will be Spark. So, well, there's actually two types of customer resources. One is called Spark application, which is like one-time Spark jobs, and there's also a scheduled Spark application type, which is for time-based applications. So you can actually run like cron schedule on for your Spark applications. So the Spark operator is basically like is a custom controller that watches these customer resources. And once it sees them, if there's any new resources coming in or there's any updates to existing resources, we'll actually take actions. So in the case of like Spark, so it will actually run Spark submit for you, so you don't need to run that manually. And once the application gets submitted, it will actually monitors the pods for the applications for you, and aggregate status into the status section of your customer resource object. So you can actually get status of your application in one place instead of like actually going through all the pods individually. So let me actually switch to the demo machine now. OK, so yeah, this is where the project's hosted. Well, feel free to take a look and try it out. So before I start, the first thing I'm going to show you actually is how an application looks like. So this is a Spark application customer resource. So you can actually see it allows you to specify pretty much every piece of information your Spark application needs. Like, what is the main class you want to use? What is the main application file you want to use? In this case, the application jar is actually hosted on GCS, and at runtime will be downloaded by the driver before it gets launched. And you can also specify the application arguments and what kind of image you want to use, and also like Spark or Hadoop configuration you want to use for your application. And then it has a section for you to specify all your dependencies. You can actually use remote dependency on HTTP servers or GCS or on your on-prem HDFS clusters. And there's also separate sections for you to specify how the driver and executor should look like. So yeah, with that. So in this particular case, actually the application I'm going to demo is a one that try to find out, on GitHub, what are the goal on GitHub project that needs help from contributors the most. So this particular application will actually reads a public GitHub dataset on BigQuery, and then writes the result back to BigQuery, and intermediate result will be written to GCS. So this is actually, it's actually interacting with both BigQuery and GCS at the same time. Okay, so the first thing I'm going to do is actually to create this customer resource object. For this, you can actually either use Kubernetes control, or the Spark operator actually also ships with a command line tool called Spark control, which makes dealing with these customer resources even easier. So what happens, like, this will actually create this customer resource to the API server. So once that's done, the customer controller will actually seize this new customer resource object, and it will actually run Spark Summit for you, and that will create the driver pod. So after that, I'm going to demo how you can actually grab logs from the driver. So you can see this is actually grabbing the driver logs. You can also do streaming. Like this will basically be there, and when more logs comes in, it will show you. You can also actually not only grab the driver log, also logs of individual executor pods. So to do that, you just use the -e option. Then you basically tell what is the executor ID you're interested in. Like in this case, if I say 1, so this actually fetched the logs of executor 1. So that's for logs. So this command line tool also comes with the status subcommand for you to actually check, so what is the current status of the app? We'll show you, the driver pod name, where the driver is running, and also, the individual states of, each individual executor pods. So you can also use Kubernetes control describe to do the same thing. We'll give you also the entire spec of your custom object as well. Okay, so the next thing I'm going to show is actually to see how we can access the Spark driver UI. So the UI is running inside the driver. To do that, I'm going to do a port forwarding from my local machine to the driver pod. So if you actually use Kubernetes control, you have to basically know what is the name of the driver pod. But if you use Spark control, you don't need to do that, because actually we know so where the driver is running. So we can actually do that automatically. Okay, so this is actually forwarding from 40402 to 4040 on the driver pod. Now if we go to, so you see the driver UI, and it gives you information about individual executors as well. So in this case, the actual stages haven't started, but this is so you get a sense how you can access the driver UI using port forwarding. So this is actually pretty straightforward. So the app is actually running on a GKE cluster here. So if I do a refresh, you can see, one driver pod got launched. Then it in turns it actually created 3 executor pods. So all of them are running. So let's stop this. And to actually, if once your app is done, you want to get rid of these pods, what you can do is actually just to do this. Then we'll delete your Spark application custom object, and in turn, all your pods will be gone after this. So yeah, this is pretty much what I want to demo today. But you can definitely check out the documentation on our GitHub site about other features that we provide. So you can actually also run cron-based applications, and also you can even actually use the Spark control command line tool to automatically ship your local dependency to GCS. So you don't have to do that manually. So what happens like, if you have local dependencies in your spec, application specification, so Spark Control will actually see them and upload them to a bucket you specify. Then we'll actually do a substitution from these local dependencies to the corresponding ones on GCS. Then submit the converted Spark application spec to the API server. So you don't need to do these kind of things manually. Everything is handled for you. So yeah, so definitely go ahead and check out our GitHub site and about documentations, those kind of things. Yeah. So we also got a Slack channel. Feel free to join and post questions or comments. Yeah, thanks. Well, next I'm going to hand over to my colleague Barney, who works on Airflow and Elasticsearch, those kind of things on Kubernetes. So he'll be giving a demo on the Airflow operator on Kubernetes. Yeah, thanks. You want us?
All right. Hi, my name is Barney. I work in Google as part of the Kubernetes team. I'm here to present about the Airflow operator. Before I tell what the Airflow operator does, let's take a look at what an Airflow is. Airflow is a platform for deploying, managing, scheduling, and monitoring workflows. A workflow is a DAG, directed acyclic graph, written in Python. So Airflow has a typical installation of Airflow has many components like the UI, scheduler, workers, and the broker, and the SQL node. So deploying Airflow is a complex endeavor with many moving parts and different configurations for each of the components. The way it's typically deployed right now is using Helm charts, but like Ken mentioned, that does not take care of the lifecycle management of an Airflow deployment. And also the developer experience with an Airflow is lacking because you need to copy the DAGs that you're developing into the cluster before you can test it out. And if you expect individual developers to stand up their own clusters, it's not an easy thing for them to do. And this is where the Airflow operator comes in. The Airflow operator is a custom resource, is a bunch of custom resources with a custom controller. What it does is it makes it dead easy and simple to deploy Airflow on Kubernetes. So I just mentioned it has custom resources. A custom resource is a declarative spec that tells you what to do and not how to do it. And there are two custom resources that the Airflow operator works on, the base and the cluster. Let's switch to the demo, and I can show you how the resources look. All right, there you go. I hope you guys can see it all increase. All right, there you go. This is the base resource. You can see the base resource has two components, a MySQL and an NFS storage. The cluster resource has the rest of Airflow components like the UI, scheduler, worker nodes, and the broker. So if you notice, the CRD spec for the base is very minimal. You don't have to specify the images or how do you bring up MySQL, how do you set up the the database inside it, the username, the root password, all of it is taken care of by the Airflow operator. All right. But you could customize the custom resource by specifying your own resource requirements or placement properties. The good thing is it just uses kubectl to create and manage these custom resources. So let's deploy this. And before that, let me start the operator. So I'm creating the custom resource. And you can notice on the logs on the left that the operator would start picking up this custom resource and deploying the stateful sets and other resources that are needed for standing it up. You see that it created the MySQL stateful set as well as an NFS stateful set, and you also see it created a secret dynamically for setting up the root password for MySQL. And the pods are ready at this point. Let's look at the other custom resource. So this is a cluster custom resource. It has, we can pick the executor of choice for Airflow. What I'm using is a Celery executor, which is a multi-node deployment of Airflow. And we use Redis as the broker, and all we need to say is which version of the image, Airflow image, that you want to use. And you also notice that there's the DAG section where you specify where the DAGs need to be pulled from. And this makes it dead simple for someone using Airflow to specify all their environment in the same file and let the operator do the deployment for them. Let's. All right. I'm creating the cluster CRD, and you notice that the operator is deploying the pods and the stateful sets. And you notice that two new secrets have been created, one for Redis and one for the scheduler. So what the operator does is it creates a database dynamically in MySQL for this instance of the Airflow cluster. So you have the UI, you have Redis, you have scheduler, and two worker nodes that are up and running. We'll give it a couple of seconds and try to access this to see if it's up. Typically, we do port forwarding to access it because it's easier that way. Voila. So your Airflow cluster is up. We can run a quick test to make sure that it's working. Run a DAG. Yeah, so these are the tasks it's running. Once it's completed, I'll show you how the DAG looks like. It's almost done. Yeah, there you go. So it shows that it ran the DAG 3 times. One is, this was triggered by me. And if you open the DAG, this is how the steps within the DAG look like. So we have deployed a working Airflow cluster within a couple of minutes, and we were able to test it. Let's take a look at the configuration here. You notice that it's set to be, the executor is Celery executor, and if you look at the connection string for MySQL, you notice that it auto-generates the username, password, as well as the database that needs to be used for this Airflow instance. And it connects to the MC-base SQL that we deployed earlier as part of the base CRD. So MC-base MySQL. All right, so I just demoed how easy it is to deploy a multi-node Airflow cluster using 2 CRDs. Let's go ahead and deploy one more cluster. All right, this time I'm going to deploy Celery with the GCS as the DAG source. Maybe I'll show how it looks like before deploying. All right, you notice it's almost similar to the earlier cluster configuration, except that you point to the GCS bucket as DAG source. right, it's deployed the second Airflow cluster. If you notice, I didn't deploy the base for the second cluster. It reuses the base from the first cluster. You could do it this way to improve resource usage. And this is particularly useful if you want disposable development clusters that you want to hand it over to the developers. Let's try connecting to the new cluster. Sorry. Has to be on site G. And this is the second cluster we just deployed. And notice that it doesn't have the state here because it's brand new. And if you look at the configuration for MySQL, let's go back here. If you notice, it has different connection string because these were dynamically generated for the second cluster. And this is how we are able to share the same base across components. Clusters. All right. Let me go ahead and deploy one more cluster. And this is something new. KDOS cluster. All right. There is something different about this cluster. If you notice, it doesn't deploy the worker nodes. It just deploys the UI and the scheduler. The reason is this cluster uses the Kubernetes executor, which does not need worker nodes to be pre-deployed. Sorry. All right, here you go. The executor is Kubernetes here. So what happens is when you run, let me connect to the new one. And all right, so let's look at the configuration for the new cluster. All right, so if you notice, it's using the Kubernetes executor at this point. And of course, the MySQL string is going to be different from the other two clusters. And all right, let's. Right, the reason. I just fired. You notice that it's generating pods on the fly. So all the tasks in your DAG will end up as pods. It's similar to the Spark operator. The good part about this is you don't need to have dedicated worker pods running all the time, and there are some use cases where it's useful. So that's the Kubernetes executor. So if you notice, the operator makes it easy to deploy Airflow with different configurations, one with Celery executor, one with Kubernetes executor, and a developer could also use the local or a sequential executor as well. And you're able to do all this with just 2 custom resources as against these many stateful sets, secrets, and all these things. And it's not just the deployment that the Airflow cluster takes care of. It also takes care of managing, day 2 operations. Like if you want to scale out, all right. All right. If you want to scale out and horizontally scale a cluster that you already deployed, you can edit the custom resource and change the replicas. So I'm going to bump it up to 4. All right, you see that it's creating the new workers for the first cluster that we deploy. So what it does underlying is it goes and bumps up the replica for the stateful set, which in turn creates new pods for you. And you could also change the executor type of your cluster once it's deployed. So for example, if you deployed a Celery executor and switch it to Kubernetes, it deletes the worker nodes for you. So it gives you that dynamic ability. And it's not just scaling and deployment, it also makes sure your clusters are resilient. What I mean by that is Kubernetes does a good job of handling pod failures and node failures, but if someone accidentally deletes your stateful set, the executor monitors that and it recreates it for you. It just makes it a little bit more resilient than just using Kubernetes manifests. What else? All right, I think that's about it. Thank you, guys.
So if there are 3 things that you want to take away from this session, they are as follows. Number 1, Kubernetes is no longer the platform for just running stateless services. You can now run complex stateful applications on Kubernetes and manage them in a very easy way. You just saw 2 amazing demos on Spark and Airflow, which could be run and managed in just a couple of minutes. Secondly, with the use of operators, you can perform day-end kind of operations, not just on Google Cloud, but on any cloud. You can run those operators on your private data centers and have the portability and the consistent experience that you want across your clouds for the business-critical multi-cloud strategy. You can discover these applications on the GCP marketplace to begin with, including the Spark and Airflow operators. And third, Google Cloud provides some of the best tools to run these applications on GKE. If you want to run an open source service, you can use Spark and Airflow. But if you want managed service with SLAs as well as production grade support, you can use Dataproc as well as Cloud Composer for these managed instances. You can integrate with some of the other GCP services like BigQuery, cloud storage, Stackdriver, GPUs and TPUs into your Kubernetes clusters. And click to deploy these applications on GKE, not just from Google, but also from third-party partners that we are working very closely with. Thank you for your time, and we welcome any questions.